Hello guys, welcome back to Mezon African Motives, still on our Mechanotechnics and for revisions, working on the bearings. We shall be considering the question paper of August 2023 that is on the application of bearings in this case. So we were given the first part on for question 6.1 to name any four equivalent loads acting on bearings. So as we understand our bearings, that there are laws that are going to affect our bearing. In this case, talking about the dynamic equivalent, the radial load, the dynamic equivalent axial load. So we have got four of them. That is the dynamic equivalent. So we have got the dynamic equivalent radial load. That is the radial load in this case. And also we have got the dynamic equivalent axial load. So it can be the dynamic equivalent axial load in this case, or we can have this as a static. We can have static equivalent of each of the given loads. So we can have the static equivalent radial and also axial in this case. So we're gonna have the radial load and also the static equivalent, the static equivalent axial load, just like the previous part on the dynamic equivalent axial load. So we can have it under a static. So these are the equivalent loads that we are going to consider in this case. All right, so that was your question 6.1. 6.2, we are given a shaft that is 630 millimeters long, is supported by two identical bearings. A radial load carried by the shaft. So take note here, we are given the radial load that is being carried by the shaft in the middle. So the one that is in the middle of 20 kilonewton, there is also an axial load of 5 kilonewton on each bearing. So there is an axial load on 5 kilonewton on each bearing. Assume that the radial and axial load factors are 0.4 and x is 0.4 and y being 1.5 respectively. So we are given neatly sketch and show all dimensions and forces for the above situation. So on this situation that we are given here, we are asked to make a neat sketch. So if we are to take note, we are given a shaft that has got a length of 630 millimeters, supported. In this case, we have given two loads. We are going to have something of this nature. In this case, we are supposed to have actually a proper diagram, but I'm just going to have a sketch in this case. All right, so connected to the other one on the other side. All right, let's just hope it is going to be clear enough, but we are supposed to have something of this nature. Okay, so in our presentation that we are given, I want us to consider these forces that we are given. We are given that this shaft is 630 millimeters long. All right, so meaning supported by identical bearing, meaning to say from this end point to the other end point, we are given 630. From our end points, in this case, we are given a distance of 630 millimeters. This is the distance that we are given, 630 millimeters. And also, we have the information about the radial load, but this is carried in the middle of, which is 20 kilonewton. This is in the middle of this whole part that we have. So meaning to say, we are going to have in between these two. So that means we have got equal distance that is taken. In this case, take note, we have got equal distance taken in between because it's in the middle. So as we are having a force in this case of 20 kilonewton, what does it mean if it is in the middle? it means if we are to apply your moments in this case, since we're going to have equal distance between these 2 points, the force is going to be subdivided into these two, okay, because they have equal distance in between. So if you are to use the application of moments, where we are to apply from a certain force here and another force, if you are to apply force times distance to this force and the force times distance using application of law of moments, you're going to see that these two forces will be equal, considering from our engineering science N3 basics of moments. So that is to mean that we are going to divide this one by 2, having 10 kilonewton this side and 10 kilonewton this side. But the presentation of a radial force is presented this way. You present a radial force going this side. So meaning to say here, we are going to have 10 kilonewton. On the other side, 10 kilonewton again, which becomes the radial force in this case of 10 kilonewton. We have the radial force. This is the radial force at the center in the middle part, but the actual radial force that is applied on the bearings in this case is what, 10 kilonewton. Having which other forces that we are given here, having also, there is also an actual load of 5 kilonewton. So the actual load, which we can write as FA, is 5 kilonewton. All right, so on the diagram, we do not consider this part. We're gonna just have these two. So the part of 6.21 is actually okay. So this information, we can use it to answer our question 6.22 in this case, whereby they need us to calculate the dynamic equivalent load. Also, remember when they asked about these loads, the dynamic equivalent load is also part of our loads in this case. So we are given these load factors X and Y from this part, the radial and axial. So meaning to say the first one, since we are working with respectively, the first one, the radial, is X. So X is representing the radial factor in this case. So we have got X for the radial factor in this case. So it goes together with the radial load in this case. So we've got X, which is being 0.4. Then for the axial load, we can check here, we've got an axial load, which is the other one now, and Y is equal to 1.5. So the 1.5 that we are given here is corresponding to the axial load in this case. So Y in this case is gonna correspond to the axial load in this case. All right, so we have got Y as the axial load factor of 1.5. So the question is, we are supposed to calculate the dynamic equivalent load. That is the one that we need, the dynamic equivalent load, which is represented or given by the formula PR in this case. All right, so having this information that we have, this is enough. If we are to check from our formula sheet, also you are given the formula for the dynamic equivalent, which is given as PR. So PR is equal to X, which is the radial load factor, times the radial load in this case, plus Y, which is the axial load factor, times its force, which is corresponding as the actual force of so we have got this. So we're going to simply multiply X for the radial load factor of 0.4 multiplied to its corresponding force, which is 10 kilonewton. So this is in kilonewton plus Y 1.5 times FA in kilonewton again. So meaning to say our answer is going to be in kilonewton, since this is in kilonewton and this is also in kilonewton. If you want, you can write this as 10 times 10 to the exponent of 3, 5, and it's up to you, or you can just leave your answer in kilonewton, and you know that your answer, the final answer that you're going to have, is going to be in kilonewton in this case. All right, so at the end you are going to obtain 11.5 kilonewton. That is the dynamic equivalent load. So when you are dealing with the loads that you're having take note the one that you are to use. You do not work with the middle part in this case, this one. You work with the ones that are applied, the 10 kilonewton applied on your axial forces, all right? So that was the application of our question. That is about 2 marks for that. As you can see, 2 marks. Just need the formula. As I said, we have this formula in your formula sheet, so you're simply going to apply that formula as it is. Then on 6.3, they gave us a condition whereby we are given, as shown in fig 4 below, the shaft load is 400. So we have got the shaft load. In this case, you are given the shaft load of 400 Newton. And the dimensions A and B are 700 millimeters, 400 millimeters, respectively. So we are given the dimensions for A and B. A here being 700. So A is being 700 millimeters in this case, all right? Then B is being 400 millimeters, the distance that are given. Calculate the bearing loads on A and B. So we have got the bearing load on A, the bearing load on B in this case. All right. How are we going to attempt such type of equation? We are simply going to use the moments concept in this case, just like our law, from our law of moments. I want you to see what is happening. These are forces that are being applied here. On bearing A, take note, it's going down, the R is going down this part. So meaning to say, if you are to consider your moments, let us just say we are having a simple sort of beam in this case. So A is going down, all right? So meaning to say we are going to consider this as a point load, all right? So this is our A in this case as our point load. Then B, it's a support, it's going up. So B, it's a support. In this case, we are considering B as a support here from our moments. Take note, it's going up. So this is taken as a support, which is given as the load support, the bearing load support. It's actually a bearing load support in this case. All right, so there is a B that we have. All right, let me just save it properly. So that is where we have our B. But knowing that there's a distance in between from this point up to this point of 700 millimeters here. So we have got a distance in between these 2 points of 700 millimeters. And also from this point to the other part that we have, whereby we have got a shaft load, we have given a distance in between. This is just your moments from your N3. So we've got 400 millimeters there. This is a point load, is facing down. The shaft load is facing down. So it's a point load. So we can put it on top as a point load. And we are given, all right, we are given the value of this. We are given the value of this load is 400. So we're given this as 400 Newton. That is the whole idea. Calculate the value of A and B, which is the loads that we have, the bearing load A and the bearing load B. So how are we going to calculate this? So like I said, we are simply going to apply your law of moments, all right? You are simply going to apply your law of moments in this case. If we are to take our moments about B, which is the support in this case, all right? So let us say we are taking moments about B, taking moments about B, which is our support. All right, we are going to see that the 400 here in this case is moving according to B, because we are taking about B. The 400 is moving this direction to B, which is the clockwise. This is, remember, the clockwise rotation. And if we are to consider A as it is moving to B, it is moving this way, which is anti-clockwise in this case. So we've got a clockwise and we've got an anti-clockwise. So we understand that the sum of moments that is for the anti-clockwise should be equal to the sum of moments of the clockwise in this case. The sum of anti-clockwise moments is equal to the sum of the clockwise moments. So which part is going anti-clockwise? A as it is going to be, and we have the distance between A and B. So we are going to have A times the distance, force times distance. The distance there, it's 700, which is equal to the clockwise moments. We've got 400, the force times the distance, 400 times 400. So there we are going to use 400 times 400. So this is what we have on the clockwise. So since we are to calculate A in this case, we can simply divide by 700, since this is a multiplication that is happening by 700 and A. So meaning to say A is going to be the product of these two divided to 700. So if you multiply these two, divide by 700, you are going to obtain 228,571 Newton in this case. So we have the force of A. If you want, you can consider again the moments, but here we can simply take now to say we have this value of A. A is a force that is a downward force. It's a point load. So we have the value of A in this case, which is a 228,571 Newton in this case. How can we find the force for B? For B, we are simply going to consider the sum of upward forces. We know that the sum of upward forces should be equal to the sum of the downward forces in this case. We need to say the force is going up, which is the force at B in this case, that is our upward force, should be equal to the downward force. These ones that are referring going down, which is the point loads, the one of 228,571 plus the 400, which is going down, the one that are going down. So this is going to give us the load at B, and that is going to be 628,571 Newton in this case. All right, so that was the whole part of our question, having 6 marks in this case. So these are the typical questions that you might be given on bearings. All we need is to work on more questions that are of this approach, whereby you can use the law of moments, the application of law of moments, and also taking the issue of forces. The sum of the upward forces must be equal to the sum of the downward forces. So that is the whole application that you can have. And also understanding, like the previous part that we talked about, whereby you are calculating the dynamic equivalent load, in this case, working with the load factors, that is the radial and the axial load factors, with the formula that you're also given on your formula sheet. So it's just an application of the formula there, which is direct. So we shall see more questions of this typical nature in our next class.